take off from A at the ground level is defined by the parametric equations of x, which is equal to 2t to the 2, and y is equal to 0.04 t to the 3, which means the distance the helicopter is from point A, and the magnitude of its velocity and acceleration when t is equal to 10 seconds. So I've already explained on how to find out the distance and also how to calculate the magnitude and directions of velocity and also accelerations in example 1. So in problem 1, we have the same situation, but this one is helicopter. I want you to try to do it at your own by using the method of solution as what is explained yesterday. And today we're going to continue on the next topic, which is called as projectile motions. Projectile motions. Or we call it as a trajectory motion as well. So in projectile motion, we are going to apply the basics method of solutions, which is rectangular XY coordinate system will be used in doing the analysis with concern about trajectory motions or projectile motions. So the motions of a projectile is involved the free flight motions of a projectile or object. The free flight motions of any object, physical body, or in this case, particles. And we are talking about the particle in chapter 2, right? So we try to convert everything from object or physical body into a particle. So it's normally studied using the rectangular components or rectangular XY coordinate system. And the projectile accelerations, if you look at this statement, the projectile accelerations is equal to AC subscript C is actually represent on the constant acceleration for the projectile, which is equal to G, which is equal to 9.81, and it is always directed downward for this G. G is equal to 9.81, directed downward. And when we do this kind of analysis, the air resistance is neglected. So actually a lot of example that we can relate with this kind of projectile motions. Let's say, for example, is when you play football or badminton or what else, any other sport which relate with the application of a ball, for example, we can relate this kind of projectile motions. When you kick the ball, it will travel. It will travel. Let's say the directions of traveling is simply like this. It will travel. Let's say we have this kind of ball. We kick this ball, applying this force, it will travel simply like this from one position to another position. Let's say this is the initial position of 1 until it reaches the position of 2. So the part of motions is considered as a curvilinear part of motion. So this we call it as a trajectory motions or projectile motion for this kind of ball. And let's have a look on this example for this one. The motion of this guy, here is some of the application instead of the one that I've already show you just now. When you kick the ball or you went to play the badminton using your racket, you push, you hit the what's so called the shuttlecock, so it will travel specific direction of motions. So all kind of things can be considered as a projectile motion or trajectory motions of a particle. So let's say we have these situations. We have a particle A which travel from A to, let's say we have another. A is actually the initial position. And this one considered as a B, for example. B is the final position. So when we want to apply this projectile motion, we need to establish the x, the horizontal direction, or the horizontal plane of the axis is this one, the x-axis, x and also y. So we need to establish the x and also y axis, and since we are applying the x-y coordinate system in doing the analysis or considering on the motion of this kind of particle based on the projectile motion. So we need to establish this x and also y, identify on the origin of O represent on the origin, and on each of these motion from initial to the final positions, we have an initial velocity of VA, and at this instance shown, probably we have the angle of theta A, which represent on the directions of the initial velocity at this instance shown. So at B, probably we consider it has the directions or the angle of theta B. So this one we can, instead of this VA X and also VA Y, for this B, we can change into VX and also VY. So we need to follow the step and step-by-step linear method of solutions. And we need to, since once we establish this X, Y as our positive sign conventions for these projectile motions, remember that the gravitational accelerations is equal to negative g, which is directed downward. It always directed downward. Establishing the positive sign convention is mean that any motions to the rightward is positive for the x, and any motion to the upward, vertically upward, is positive. So that is the positive sign convention. So once you consider all this kind of thing, the next step is what you need to do is you need to apply the constant acceleration equations. Let me add several blank slide so that I can explain further on this how to do the procedure of analysis when we deal with this kind of projectile motions. Okay. Okay, let's say we have this procedure of analysis. Analysis for projectile motions. So let's say I'll start with these illustrations. So So we have a particle, let's say we have a particle, in this case, we have a particle A, for example. Small letter of A represent on the particle A. And here is the initial velocity. So we have this VA. The dotted line, the curved dotted line represent on the path of motions of this particle from A to the final position, which is considered as B, for example. The origin is O. So from O to A, it has what's called horizontal distance of XA, and from O to B, it has a horizontal distance of XB, and from O to A, it has the vertical distance of YA, and from O to B, it has the vertical distance of YB, for example. So this one that we need to establish first, and it has a direction of let's say theta A, and when it reach at B, we assume that it has the final velocity of VB. And if we expand, since we are applying the rectangular of x-y coordinate systems, so we need to break it down into the component of x and also y. So we're going to have this v bx, and also we have v by. Similarly to this one, we have this is A, the particle A. It has an initial velocity of VA. If we break it down into the component of x and also y, we're going to have this V A x, VAX, and also VAY. Okay. Normally, the initial velocity is given in the questions. Normally. So we can try to calculate or to find out this what is the final velocity of VB, what the time of flight from A to B, for example. So this is the one that you need to establish first. Normally they will give you the what so-called the problem with the appropriate what so-called figure or gambar raja, so that from that you can do the illustrations, identifying on the initial and also the final velocity, what is the distance of x, horizontal distance and also the vertical distance at E and at B, at the initial and also at the final positions. A is initial. Initial position. B is the final. And remember that the gravitational acceleration of G is always directed downward. So we have this G, which is directed downward. So our positive sign convention is positive to the rightward for X and positive to the upward for Y axis. So these are our positive sign conventions. So when you do this kind of illustrations of step one, what you need to do is illustrate final positions. And then step 2 is establish positive sign conventions. Establish positive sign conventions, illustrate the particle initial and also final positions, and then break down initial, break down initial and final velocity into the components of x and y. Step 4 is apply constant accelerations equations. What do I mean is you need to apply this what is constant acceleration equation. We have three equation of v. This is the first one, v is v naught plus a t. The second one is v square is equal to v naught square plus 2a s minus s naught. And the third one is s is equal to s naught plus v naught t plus half a t to the 2. So applying these constant acceleration equations into the component of x and also y respectively. In component x, it means that we need to apply the based on horizontal motions. In component y, we apply this equation based on vertical components or vertical motions. Consider on horizontal motions. It means that this positive to the rightward for these horizontal motions. So persamaan dia adalah, what is the equations? You need to go back to these illustrations. Applying these three equation of v, step number 4, v is equal to v naught plus at, v square is equal to v naught square plus 2a, s minus s naught. And the third one is s is equal to s naught plus v naught t plus half a t to the 2. Let's consider on the first one. V is equal to v naught plus at. So if we consider on these horizontal motions, everything need to be put into this x component, x direction. So v at b, vbx is equal to v a x plus a x t between a b. tab represent on the time of flight from position A to position B, from initial position to the final positions. So TAB. So ni ada persamaan between this one and also this one. We consider everything in the x component. X component for this final velocity is vbx. x component for the initial velocity is VAX. AX, remember that when we talk about this, another one thing which need to be considered is AX is equal to 0. There is no accelerations in the x direction, in the horizontal direction. The only acceleration is gravitational acceleration for the free flat motion, which is always directed downward, and it is equal to 9.81 meter per second. So we have VBX to VAX plus AX TAB. Since AX is equal to 0, then therefore VBX is equal to VAX. So we got the first one, first equation. And then let's consider on the second equation, which is V square is equal to V naught square plus 2A S minus S naught. The second equation. As we relate with our illustrations, so we're gonna have VBX to the 2 is equal to VAX to the 2 plus 2AX S minus S naught. In the X directions, we have, look at this one, XB minus XA. So it's become X XB minus X. So we can write it down as X B minus X A. So this one AX is equal to 0. So apa yang akan tinggal adalah VBX to the 2 is equal to VAX to the 2. So if we simplify this, we can get this VBX is equal to VAX. Similar with the first one. Bolehlah letak satu dulu Then we need to consider the third equation of S is equal to S naught plus B naught T plus half AT to the 2. Consider everything in the X component or in horizontal direction or horizontal motions. So we gonna have for this S, kita akan dapat this XV is equal to X XA plus VAX TAB plus half AX TAB to the 2. Since AX is equal to 0, the equation become XB is equal to XA plus VAX TAB. The time of flight from A to B, from initial position to the final position. So we got another one equation. Let's consider on equation 2. So we consider all this in horizontal motion. See, horizontal motion we can obtain two equations, which is the first one is VBX equal to VAX. Second one is XB is equal to XA plus VAX TAB. Okay. And then step 6 is considered in vertical motions. Step number 6. So in vertical motion, our positive sign conventions for the vertical motion is positive upward. Positive upward. So we consider the equation of V is equal to V naught plus A B. So the first equation. So in what so called in the y directions, so it becomes V by is equal to VAY plus AY TAB. So in this case, AY is equal to negative G is equal to 9.81. Why negative G? Because it is directed downward. Our positive sign convention is upward for this one. So we need to put this positive sign convention for the first equation. Similarly to the previous one, we need to consider on this positive sign conventions of the equations. It is positive to the rightward. Similarly to this one, positive to the rightward. So what we need to do is to substitute this AY is equal to negative G into these equations. And therefore, we got this V, Vy, our positive sign conventions, is equal to V, Ay minus G multiply with TAB. Okay. So let's consider this in the previous one, we got this equation 1, 2. Continue. Let's consider this one as an equation, the third equation. And then we continue to the next equation, which need to be considered, which is V square is equal to V naught square plus 2AS minus S naught. Try to relate with this our illustrations by considering on the vertical motions. So we're gonna have this V By to the 2 is equal to V Ay to the 2 plus 2 minus G S minus S naught. So this one is YB minus YA. YB minus YA. Yes, YB minus YA. So YB minus YA. This one. Therefore, VBY to the 2 is equal to VAY to the 2 minus 2G. G represent on the gravitational acceleration, which is equal to 9.81. Multiply with YB minus YA. So we got the another equation. Let's consider this as equation 4. And let's consider on the last. The last equation is S is equal to S naught plus V naught T plus half AT to the 2. So let's consider on the Y direction for each of these. So it's become S minus S naught. S minus S naught. This one is YB. YB is equal to YA plus VAY TAB plus half negative G T A B. So the equation becomes YB is equal to YA plus VAY TAB. AY and also AB is a subscript for this one. Minus half G TAB. So we got 5 equation altogether, the 5th equation. So when we consider on these projectile motions, there are 5 equation altogether. You don't have to memorize everything. So the important thing is put in your mind that the basic equations which need to be used in doing the analysis of this projectile motion is constant acceleration equation. 3 equation of constant acceleration equations. What you need to do is you need to expand this equation into the component of x horizontal directions and y vertical direction respectively. And by expanding this kind of equation, we got equation 1, 2, 3, 4 until 5, the one that I have already show you just now. So this is the method of solution or the procedure of analysis when we deal with this kind of projectile motions. So of course you need to come up with the free body diagram initially. So the free body diagram, the first one, this one is free body diagram. Let's consider this as a free body diagram, FBD. You need to illustrate all this kind of thing, expand it into the component f as x and also y respectively. Then we can proceed applying the constant acceleration equations, and through that we can solve the problem which concern about these projectile motions. You can calculate the component of velocity, initial velocity in the x in the y directions if what's so called the initial velocity is given, and we can find out what is the component of velocity in the y and also x direction for the final positions, and you can find out what is the magnitude of velocity in the final position as well as the directions of velocity. And we can also identify or determine what is the time of flight from initial to the final positions, the traveling time from A to B, from traveling time from A to B, initial to the final position. You can also find out this as well. Of course, you need to illustrate, come up with this free body diagram, identifying on this one O represent on the origin, the vertical, the horizontal distance of initial position, also the final position of XA and also XB respectively. Similarly to this in the Y directions. Is there any questions? So this one is actually represent on the illustration which is available in this slide. So look at this one, dia akan dapat persamaan yang sama juga sebenarnya. Akan ada how many equation altogether? 5 equation altogether as well. Satu, dua, and the previous one is 3. This one is equal to this one, VAX, VA cos theta. 3, 4, and 5 altogether. So yang ni dia represent gambar rajah yang ada di dalam slide ni yang saya tunjukkan dalam photo tu, previous one. It's based on my illustration and my illustrations. When we consider on the motions of any particle or object when it travel from initial to the final positions. Sama je sebenarnya ni. Yang ni sebab Y dia ada komponen of dalam komponen X dan juga Y, dia nyatakan ada this equation of application of trigonometry function of VA sin theta and also VA cos theta and also VA sin theta. So yang ni sebenarnya dia expand. Let's say for this VAX dia akan jadi VA cos theta, for example. The component of velocity in the x direction or the initial velocity ataupun the final velocity. This depends. Okay, we continue with this example 2. Example 2. So the example 2 is concerning about the projectile motions. So the question is the chipping machine is designed to eject wood at chips V0 is equal to 7.5 meter per second. If the tube is oriented at 30 degrees, so this tube is oriented at 30 degrees at this instant shown as the angular position of theta which is equal to 30 degree. Determine how high h. Dia nak tahu apa itu ketinggian h. The pile timbunan rumput ni. How high h the chips strike the pile. The chips strike the pile if they land on the pile 6 meter from the tube. So the horizontal distance between O to A, between initial to the final position is equal to 6 meter. And they ask you to find out what is h, ketinggian h tu. And this instant shows. So data yang diberikan adalah ketinggian daripada ground up to this muncung. The chipping machine punya nose, the distance from ground up to this nose of this chipping machine, which is equal to 2.1 meter, and the initial velocity is 7.5 meter per second, and the directions or the angle is equal to 30 degree. Then we can find out the component of velocity in the initial position. So here is the method of solutions. Three unknown h, time of flight, TOA, and the vertical component of velocity, which is VAY. Okay. Taking origin at O for initial velocity of a chip. So diberikan initial velocity is equal to 7.5, and through that data which is given, we can find out what is the component of initial velocity in the x and also y directions. So kalau kita lihat gambar rajah ni, 30 darjah sudut dia, initial velocity adalah 7.5 meter per second. So kita pecahkan dalam komponen X dan juga Y, kita akan dapat VOX dan juga VOY. VOX is equal to 7.5 cos 30 degree, which is equal to 6.5 meter per second. To the right word. VOY is 7.5 sin 30 degree, is equal to 3.75 meter per second upward. Okay. And Daripada sini kita boleh tahu, we can calculate what is VAX. Bila dia just reach at A of the pile, before it's what's so called stop, before it stop, the final velocity is VAX. So we know that VAX equal to VOX. Kalau kamu masih ingat persamaan yang saya terbitkan tadi itu, persamaan yang pertama, the first equation is VAX. Kalau yang tadi dalam illustration tu, dalam tu, this one. Bila kita dah establish ni, kita akan dapat first equation adalah VBX. VBX is equal to VAX. Ni dekat saya punya illustration lah. VBX is equal to VAX. Dia sama je sebenarnya, konsep dia sama. So yang ni adalah the final horizontal velocity is equal to VAX. The initial horizontal velocity is VOX. Since VAX is to VOX, therefore VOX kita perolehi pada step yang awal tadi tu, yang ni. So VOX is equal to 6.5 meter per second, and therefore VAX also equal to 6.5 meter per second. So the horizontal velocity for the initial and also the final positions is equal. Is similar. Each will has the same horizontal velocity, the component of velocity in the x directions. And we know that AY is equal to 9.81 meter per second square. So dia akan lakukan step yang seterusnya lah. The horizontal motions, the equation which need to be considered is xa is equal to x naught plus v naught x TOA. The time of flight TOA, which is equal to this is the one that you need to find out what is the TOA. XA kita dah tahu, X naught also we know. Then VOX diperolehi daripada kaedah yang tadi itu, kaedah yang sebelum tu. Then through this we only have one unknown, which is TOA. So TOA is equal to, because sendiri, which is equal to 0.9231 second. You masukkan maklumat yang berkaitan dalam persamaan this one. So at the end, you've got this TOA is equal to 0.9231 second. So if you look at this one, in order to get the answer for this H, which is equal to 1.38 meter at the end, we need to follow this step by step line. Initially, you need to find out what is the initial velocity. So the initial velocity is given, what is the component of initial velocity, and then through that we can find out, you can calculate what is the final okay, this one, VAX is to VOX. So the initial and also the final, it has the same horizontal velocity. And then once we consider all the horizontal components of velocity, ada dua persamaan yang kita pakai tadi tu. So bila kita dah guna pakai, kita akan dapat maklumat yang lebih terperinci. You can find out what is the time of flight from A to O dan sebagainya lah. Okay, in vertical motion, relating TOA to initial and final elevations of the chips. So by using this equation, y is equal to h minus 2.1, which is equal to y naught plus v naught y TOA plus half A T TOA. So in this case, AC is equal to 9.81 meter per second square. Okay. So once you substitute whatever the data into these equations, at the end you got the answer for H, which is equal to 1.38 meter. 1.38 meter. And then through that we can calculate what is the initial, what is the final velocity of VA, and also the directions of velocity at A just before it hit the pile at A. The ship just before it hit the pile at A, ini adalah dia punya result dan keputusan yang diperolehi lah. Is there any question? I want to show you the other method of solutions for this example. Example apa ni? Example 2. So dekat sini, if you look at this one, dia punya origin is at O. Kan? We can put the origin at the ground as well. I will show you after this. Instead of considering that the what so-called the origin is at O, which is equal to the position for the initial velocity, doesn't matter. You can also put this initial at the ground. Okay, is there any questions?
Okay, sir.
Okay, saya cuba tunjuk cara yang satu lagi lah. Let me add a blank slide first. So example 2. So the first one, of course, FVD. You need to draw the free body diagram. Simply like this. So this P, this one is O, V naught is equal to 7.5 meter per second. The angle is equal to 30 degree. So here's the ground. Let's travel like this until it's reached the pile. What is the height of this pile? You do not know. You need to okay, this one is the height of this pile is YA. Ini adalah. So O, this one is A. Ini adalah A. So let's say here is the our cost, our origin. Origin. Let's say we consider as a B. B is the origin. So from B to A, it has a distance of XA lah, XA, which is equal to 6 meter. So X A X B is equal to 0. Okay. So the height from B horizontal line until this height of this O is equal to 2.1 meter. Okay, for this one, ini adalah YO, and then this one is YA. The initial also called height YO at O, and the final height of the particle is at A, which is the height is at YA. This shows. So this one is axis of X, axis of Y. So once you illustrate this, what you need to do is this one is a little bit different from the previous method of solution, where in the previous method of solution they assume that O represent on the origin, but this one is the origin is at B. You can put this way as well, at B. So the next step is step 2. Consider horizontal motions. Horizontal motions, and AX is equal to 0 meter per second square for the horizontal motions. So the basic equations, V is equal to V naught plus A T. So the equation that we need to consider on the horizontal direction is, it becomes VAX is equal to VOX, and VOX is equal to 7.5 cos 30 degree. So 1.5 cos 30 degrees. So you got this 6.5 meter per second for this VOX. Therefore, VAX equal to VOX is equal to 6.5 meter per second. Then we consider on the second equations. Let's consider on the second equation, which is S is equal to S naught plus V naught T plus half AT to the 2. So ini akan jadi XA is equal to XO plus VOX TOA plus half A X T O A. So since AX equal to 0, then kita boleh terus potong lah. So dia akan jadi XA is equal to XO plus VOX TOA. Let's consider this one as first. Yang ni adalah second. So what you need to do is the next step is since okay, the next step is substitute whatever the data which is obtained from the previous so-called calculations, if any. So in this case, XA is equal to 6 meter, XO, X naught is equal to 0 meter, plus VOX is equal to 116, sorry, VOX is equal to 6.5, and then the unknown is only TOA. Therefore, 6 is equal to 0 plus 6.5 TOA. And therefore, through this, we can calculate what is the TOA. 9.9231. Okay, that is the initial step. And through this, we can find out what is the time of flight from O to A. Okay, finish the step, first step. And then what you need to do is consider on the vertical motions. So vertical motions, consider on the first equation of V is equal to V naught plus ACT. So dia akan jadi VAY VOY minus G TOA. This one is TOA. So what you need to do is you just don't forget to put the positive sign convention, positive upward for this one. So if you expand this one, what you can get is, you know that V O Y is equal to 7.5 sine 30 degree. So that one is equivalent to 3.75 meter per second. So just substitute into these equations. VAY is equal to 3.75 minus 9.81. Let me erase first. 3.75 minus 9.81 multiply with TOA, which is 0.9231. So in this case, we only have one unknown, which is VAY. So when we solve this one, VAY is equal to minus 5.31 meter per second upward. So since it is negative, our positive sign convention is upward. So makna dia akan, it is equal to VAY is equal to 5.31 meter per second. It is actually directed downward. Okay, you got this VAY, then we go to the next step. Let's consider on the other equations. Which is this one and this equation. Let's consider on V square is equal to V naught square plus 2A S minus S naught. So this is the basic equations. But we consider on the Y directions. Y so it's become VAY to the 2 is equal to VOY to the 2 minus 2 9.81 YA minus Y naught. And for this one, we substituted whatever the data which is obtained from the previous method of solutions, which in this case VAY ialah sama dengan negatif 5.31 plus 2 close bracket is equal to VAY and VOY is equal to 3.75. Okay. Minus 5.3 to the 2 is equal to 3.75 to the 2. Minus 2 times 9.81 YA minus 2.1 minus 2.1. So you look at this one, we only have one unknown, which is YA. So when you solve this one, YA is equal to 1.38 meter. So we got the same answer as the previous one. Okay. The only difference between the first and also the second one is how do we fix the positive sign conventions and fix the origin, fix the origin of this free body diagram, origin of O, where I fix it on the ground for this one. So we can directly find out what is YA. Okay. And from this you can what so called calculate or determine the magnitude of velocity when it reach just before it hit the pile at A. Just before it hit the pile at A, we can identify or calculate what is the what's so called magnitude, also the directions of the velocity of at A at the final positions. Is there any questions, class? So dekat final position,
No, sir.
macam ni. Kat sini tadi VAY kita dah dapat, which is 5.31. Let me do the illustration for this one. So ni adalah dekat O. Ni adalah A. Ni adalah pile. So they travel like this. So at A ni, kita kena pecah dalam komponen of X dan Y as well. So we have this VA, we have this VAX dan juga VAY. Ni VA, this one is theta A. So VA is equal to square root of VAX to the 2 plus VAY to the 2. And VAX is equal to, lihat balik solusi yang sebelum tu, VAX is equal to VOX is 6.5. 6.5 meter per second. VAY is equal to 5.31. 5.31 meter per second. So yang ni adalah to this direction dan ni adalah direction ni ke bawah lah. So what you need to do is just substitute 6.5 to the 2 plus 5.31 to the 2. Then we can find out what is the magnitude of velocity of the chip when it's traveling until it reach point A. Just before it hit this point A, it has the velocity of 8.39 meter per second. Dan ini adalah magnitude. Directions of velocity, which is theta A. So tangent theta A is equal to 5.31 divided by 6.50. Therefore, theta A is equal to, you got the answer. You calculate this one, you got the answer, which is equal to 39.25 degrees. So the directions of velocity, theta A is equal to 39.25 degree. Okay, is there any questions for this method of solutions?
No.
Okay, we have a problem to this problem is actually can relate with the application of normal and tangent coordinate systems. So when we continue with this normal tangent coordinate system on next Wednesday pula. Monday, uh, you can try to solve this problem by using the method of normal tangent coordinate system. And bear in mind that you have the first test by next week until the topic of normal tangents. If possible, then I will share with you the recorded versions of this normal tangent punya slide apa this lecture 4 lecture 4 before by this week inshallah so that you can refer to that kind of recorded versions, especially regarding this lecture 4